Hello, today I'm going to talk to you a little bit about enthalpy. And so thermodynamics is a big topic in chemistry. Today we're just going to talk about one portion of it and then just one way to calculate that quantity. There's a lot more to it, but you wouldn't get to that in this class. We would cover that in AP chemistry if you take that. So enthalpy is a measure of the heat transferred in a process, usually in a chemical reaction, and under constant pressure. And the reason that we do it under constant pressure is because that's what we have in the lab usually. So that's just what it means. But you can just think of it as a change in energy or the flow of heat during a chemical reaction. Right, so there are two different kinds of reactions that we're going to talk about in terms of enthalpy. There are exothermic reactions and then endothermic. So exothermic is when our system moves from a low potential energy, moves to a lower potential energy from a higher one, and in the process releases energy into the surroundings. So basically, your reactants have a fairly high potential energy, and then when you're finished, the products have a lower potential energy. And you could also see this as having a hump in the middle that would represent that activation energy that we talked about when we did kinetics. All right, and even though it's a little counterintuitive, but even though the system, our chemical reaction, has less potential energy when we're done, because it released energy, the surroundings, or what you actually feel, either the solution it's in or the test tube that it's in, is always going to feel warmer when you have an exothermic reaction take place, all right? And the other thing is we store potential energy in bonds. All right, and so when we form bonds, we always are doing an exothermic reaction. So we move to a lower potential energy when we form bonds, which is favorable. All right, the other option is an endothermic reaction where we move to a higher potential energy. So in order to get from that low potential energy to a higher one, we need to absorb energy, or the system needs to absorb energy from the surroundings. And so because of that, the reaction will feel cold or cool when we do it in a test tube or in the lab. All right, so in this case, breaking bonds always requires energy, and so that's always going to be an endothermic reaction. All right, so now let's talk about bond energies really briefly. So bond energy is just the amount of energy that's required to break a bond, or the amount of energy you get back when you form a particular bond. So you'll notice if you look at the chart that's here, or the one that's in your note packet, that single bonds, like an OO single bond, have smaller bond energies than equivalent double bonds, okay? And then if you were to go from, a single bond to a double bond to a triple bond, it would even be a higher bond energy. All right, so you can see that the NN triple bond has 946 kilojoules per mole bond energy, which is very high. Okay, so how are we going to use these bond energies? We can use this information to figure out what the enthalpy for a reaction is. So I said if we break bonds, it's always endothermic, and if we form bonds, it's exothermic. But in most chemical reactions, we do some of both. So for example here, we have to break some HH bonds and an OO bond in order to have those atoms available to reform new bonds to make water. So we do both breaking and forming, right? But we can add up the energy required to break the bonds in the reactants and the energy to form that we get back when we form bonds in the products, and compare them and figure out the enthalpy of our reaction, or the delta H. That is the symbol that we use for enthalpy. Okay, so in order to know what kinds of bonds we're breaking, we first need to draw the structures. Okay, so in this reaction, we have two H2 molecules. So I drew two H2 molecules. All right, and we have an O2. It's important here that you get the structure correct, because remember I said an OO single bond is different than an OO double bond. And O2, the bond that holds them together, is a double bond. Right? So now let's look at our chart, and let's figure out what is an HH single bond. Right? So that's here on the chart. One of those is 436 kilojoules per mole. All right? We have two of them. 1, 2. All right? Each connection is one bond, right? So 2 times 436, that's what will be required to break up those hydrogen molecules. And then if we do the same thing for oxygen, it's 498 for one OO double bond, okay? so 498 there. Add those two values together and you get 1,370 kilojoules per mole to do the two HH bonds and the OO double bond. All right, now let's do the same thing for the products. So we form two water molecules. All the water molecules have the same kind of bond. There's an OH bond, an OH bond, an OH bond, and an OH bond, right? They're all the same. And an OH is the same as an HO. Doesn't matter the direction, okay? So this is one of the reasons it's important to draw them, because you might not realize looking at this that you've got 4 bonds. Okay, so an OH bond is 467. So to break all 4 of those, it will be 1,868 kilojoules per mole, and that will be energy released because we're forming bonds. So now let's compare them. So for the net energy of the reaction, it's always going to be the energy absorbed by breaking bonds minus the energy released by forming bonds. All right, and in this case, we get negative 498 kilojoules per mole. All right, that negative means that we have an exothermic reaction. So if your delta H is negative, then you have an exothermic reaction. All right. Now let's do one more example. An N2 and an O2. We already know what the O2 looks like. N2 in molecular form is a triple bond. All right, and O2 we know is that double bond. All right, let's look at our table. The N triple bond is all the way down here. It's 946 kilojoules per mole. The OO is here, it's 498, all right? And if we add those together, that's 1,444 kilojoules per mole that's required in order to break these two bonds, all right? So that's a lot of energy. Now let's do the products, all right? So we form two NO molecules. They're both, they're the same, but each of them is an NO double bond. So if we go to our table, an NO double bond is 632 kilojoules per mole, and we have 2 of them. Right, so that's a total of 1,264 kilojoules per mole. I just did the math in my calculator. All right, and now if we compare them, absorbed minus released, 1444 minus 1262 gives us a net energy change of 180 kilojoules per mole. All right, the energy absorbed is bigger, all right, which is why we have a positive number, all right, which means this is an endothermic reaction. Okay, so these are the only kinds of calculations we're going to do in this lesson, and you also need to be able to know that if we break bonds, it is endothermic, and if we form bonds, it's exothermic.